Some students do not appreciate mathematics and science simply because they think it has no direct applications in real life. So in today's video, we are going to solve real-life problems using mathematics and science. So kindly please get your pen, paper and calculator, and let's study together. Problem number 1. A man standing on a bridge throws a stone straight up. Exactly 5 seconds later, the stone passes the man on the way down. And 1 second after that, it hits the water below. Find the height of the bridge above the water. The equation of free fall of an object under the influence of gravity alone is given with the formula S is equal to S sub 0 plus V sub 0 times T minus 16 T squared, where S sub 0 is the initial position and V sub 0 is the initial velocity at time t is equal to 0. Remember, the problem states that when t equals 5, S is equal to S sub 0. So let's substitute these values and solve for the initial velocity V sub 0. Now we solve for the height of the bridge S sub 0 using the same equation, but using the time t equals 6 and V sub 0 is equal to 80. Notice this. The value of S is equal to 0 because the stone is in the water already. So by substitution we have so the height of the bridge is 96 feet. Problem number 2. A railroad track crosses a highway at an angle of 60 degrees. A train is approaching the intersection at the rate of 40 miles per hour. And a car is approaching the intersection from the same side as the train at the rate of 50 miles per hour. If, at a certain moment, the train and car are both 2 miles from the intersection, how fast is the distance between them changing? Looking at the figure, this problem involves geometry, trigonometry and calculus. The problem is asking about how fast is the distance between them changing. In the figure, the distance between them is u. If the distance is changing, then that means the derivatives of u are du. So let's derive an equation that will contain the value of du. By using the figure, we can only use the law of cosine to derive an equation containing u, and then we solve for its derivative. Using the figure, we write the cosine law. Using a calculator, we get the value of cosine 60 degrees is equal to 1/2. We will substitute it to the equation and simplify it. Then, we solve for its derivatives. Looking at equation 3, we can see that there are still two unknowns, u and d, u. Let's solve u using equation 2 because x and y are already known. We substitute the value of x and y to equation 2 to get the value of u. Then by using a calculator, we can solve for the value of u. Now that we have all the values, let's substitute them to equation 3 and solve for du. So the distance between the car and the train is changing at the rate of 45 miles per hour. Problem number 3. A farmer wishes to fence in a rectangular field of 10,000 square feet. The north-south fences will cost $1.50 per foot, while the east-west fences will cost $6 per foot. Find the dimensions of the field that will minimize the cost. Now let's analyze the problem. We are required to get the dimension of the field that will minimize the cost. Therefore, the value of x and y. Let's derive some equations that will contain the value of x and y. Using the area, x times y is equal to 10,000. Now let's call it equation 1. Since there are two unknowns, we need also two equations to solve for their values. Now, let's derive another equation. Remember that the problem mentioned about the cost, so we will derive the second equation using the given costs. In this problem, we are talking about the fence of the field. Therefore, we are talking about the perimeter. So we will derive the cost based on the perimeter. The problem requires the dimensions of the field that will minimize the cost. Remember, the keyword here is the cost, that is, to be minimized. That means we will solve for the derivatives of c with respect to any of the dimension, let's say x. Earlier, we derived these two equations. So, before we solve for the derivatives of c, let's substitute the value of y in equation 1 to the y in equation 2. In doing this, equation 2 will now only contain one unknown, which is x. Let's transform equation 1 to this form. After that, we substitute the value of y to equation 2. Then solve for the derivatives of c with respect to x and equate it to 0. Equate the derivative to 0 and use a calculator to solve for the value of x. Substitute the value of x, which is equal to 50, to equation 1. Then solve for the value of y using a calculator. So, the dimensions of the field that will minimize the cost are 50 feet and 200 feet. Problem number 4. A boy is flying a kite, which is at a height of 120 feet. The wind is carrying the kite horizontally away from the boy at a speed of 10 feet per second. How fast must the kite string be let out when the string is 150 feet long? In this problem, the required is the speed of the string to be pulled by the boy. Looking at the figure, it is the change in u, or in other words, the derivatives of u. So let's derive a formula that will contain the value of the derivative of u. We have derived equation 2, which contains the required, which is derivatives of u or du. For us to get the value of du in equation 2, other variables must have values as well. By inspection of equation 2, the only variable with no value yet is x. So let's solve for x first using equation 1. Using equation 1, substitute the value of u and y in the equation to solve for x. Then solve it using a calculator. Going back to equation 2, we can now solve for the value of du because all other variables have their values already. Let's substitute them to equation 2 and solve for the value of du. So, the kite must be let out by the boy at 6 feet per second. Problem number 5. A man in a rowboat at p. 5 miles from the nearest point A on a straight shore wishes to reach a point B, 6 miles from A along the shore. If he wishes to reach B in the shortest time, where should he land if he can row 2 miles per hour and walk 4 miles per hour? The problem states, if she wishes to reach B in the shortest time, where should she land if she can row 2 miles per hour and walk 4 miles per hour? This means we need to get the value of distance x by solving for the derivatives of time t and equating it to 0. So, we need to derive an equation that contains the time t and the distance x. In the figure, the total time is the time rowing plus the time walking. We are given with the distance and the speed. And we are required to get the time, t. Can you recall any formula with this situation? If we can recall physics, speed v is equal to distance d divided by the time t. Rearranging the formula, we have time t is equal to distance d divided by the speed v. Now let's solve for the distance he rowed and the distance he walked. So now that we have all the values, let's substitute them to the equation. To simplify, we can also write this equation to this form. Then we solve for the derivatives of t with respect to x. We continue solving, simplify the equation, and equate it to 0. After that, we solve for the value of x. To get rid of the square root, we raise both sides of the equation to 2. And then, continue solving for x. Therefore, the man should land at x equals 2.89 miles from point A. That's all for today. Thank you for watching, and see you all again in the next video. Goodbye.